Yeah, so I'll do a brief, on last, 2 weeks ago on Thursday, I continued a little bit with the lecture, so I'll briefly review this. So this is about paragraph 6, representations of semi-simple algebras. So what's the setup? As always, we fix a semi-simple Lie algebra, an H a Cartan subalgebra, and then V a representation for G, and if we restrict the representation map from G to H, then we have this nice weight space decomposition that V decomposes into weight spaces V lambda, where lambda is formally, is sum over all elements of the dual of the Cartan, but in fact only finitely many of these summands will be non-zero. So, and what one likes to know, of course, is the dimension of these spaces. So, general question. Given, all the data are above, G, H, V, usually in a discussion G and H are fixed, and then additionally we are given a representation and a weight, lambda. What is the dimension of the corresponding weight space? So just to give you an idea how an answer might look like in the most basic example we looked at, if G is SL2, then we had this dimension Vk. This representation Vk, so this consists of homogeneous polynomials and two variables, total degree k. And then we had these weights, say L times omega. So what's the dimension of this vector space? Well, we've seen that this is either 1 or 0. The weights of this vector space were k omega, k minus 2, L, k minus 2 omega, k minus 4 omega, and so on. So how do I express this in these coordinates? Let me just let me just change the coordinates. K minus 2 L omega. So this is 1 if L is something from 0 to k, and 0 otherwise. So this is example answer. So here it's easy, or we just studied this example so well that we can just write it down. But in general, this will be more difficult. So in order to study this sequence, so this is a family of numbers parameterized by this lambda, And so we use a standard trick and introduce generating functions. So this is the character of V, and this is just the one way to define a generating function. So this would be the sum over all lambda in, I can also take all linear forms on H and just take the dimension of V lambda and write e to the lambda. And again, so everybody agrees that this is the character, but there are different interpretations what this is. So you can view this as an element of the formal group algebra CP. Remember, P was the set of all weights occurring in any G module. So in particular, in this one we chose, there won't be other weights occurring than the ones in P. So I can also just write for the sum lambda in P. So this is a lattice in this vector space H star. And so this is the algebra of formal linear combinations of elements of the form e to the lambda, where lambda is an element of P, and with a naturally defined product. Or you can view this as a function on the Cartan algebra, just by to evaluate an element, to evaluate such a function on an element of the Cartan. I just evaluate the lambda in the exponent on this element, and then there is this is the regular exponential function e to the some number. So these are the characters. So that was definition 6.1. Okay, so let's do something new now. So now we are aiming at the classification of irreducible G modules, G representations. So here I'll only give the results, no indication of the proof. Well, you'll see. Now we fix the base. Now recall we had this Lie algebra and a Cartan subalgebra, and to this we associated a root system phi. This was a subset of the dual space for the Cartan. So this was this, which we visualized as a point configuration, but which was just the set of weights of the adjoint representation. And then there was this theorem that you can always find a base. So this is a basis of H star, which is particularly nice. Namely, all the roots can be expressed as linear combinations with integral coefficients of elements of delta. And in any such linear combination, either all the coefficients are non-negative or non-positive. So that was a base. So I denote by phi plus. In phi, well, as I just reminded you, we have this property that every root in phi has either all non-negative or all non-positive coefficients with respect to our base delta. So then phi plus is just the set of roots with non-negative coefficients. So what else do we need? So this is the definition part. So these are called positive roots. So far so good. So what do we need them for? We fix an irreducible representation, G, irreducible G module, and then the theorem is the following. There is a uniquely determined element lambda in P such that lambda plus alpha, such that two properties should hold. First one, lambda is a weight of V. Again, that means just by definition, the dimension of V lambda is positive. But if I add any positive root, then I don't get. So for all positive roots, lambda plus alpha is not a weight anymore. And again, definition, this lambda is called highest weight. Yeah, so again, if you did the exercises, this will not be too astonishing, or at least, well, maybe it's astonishing that it generalizes, but this is very similar to a phenomenon you saw already. So when we, I think this was in this weird proof where we showed that all eigenvalues of SL2 elements, of SL2 representations, of the H eigenvalues in SL2 representations are integers, then we constructed explicitly such a highest weight and found a highest weight vector. So now maybe I just draw some more pictures so you have some pictures in your mind. Examples. So if our Lie algebra is SL2, so what's the root system? That's minus 2 omega and 2 omega. And we fix, well, the canonical choice somehow, well, it's not canonical, but the usual choice is to fix as a base the 2 omega So this is also the set of positive roots here. So, right, so there are these two roots, minus 2 omega, 2 omega, and we just pick that to be the positive one. So what are the weights of, say, Vk? Well, we just revised this in the beginning of the lecture. So these are, the weights are k, omega, k minus 2, omega, and so on, up to minus k, omega. So what can I... so there is only one positive root to check, so I have to find the dot here such that when I go 2 to the right, I won't obtain a dot anymore. So this is the unique element which has this property. So this would be the highest weight here. Or let's consider one more example. Mainly the only other example we studied in detail, the adjoint representation of SL3. So G is SL3, V is the adjoint representation. So what's phi was, that consisted of these epsilon I minus epsilon j vectors, which I just, I just draw the picture now because I think we know by now the thing. So these are these 6 vectors. And I think, here the canonical, or not the canonical, but the usual choice is to take these two as a base. So say alpha 1, alpha 2, and then these 3 form the set of positive roots with respect to the base. So whenever I'm saying something which is weird, just tell me. That should be all clear. So what are the weights of the adjoint representation? Well, these are, of course, the roots by definition, and also 0. Huh? Remember, we defined the roots to be the non-zero weights of the adjoint representation. So if we consider the weights of the adjoint representation, then we have to put 0 back in. So what's the highest weight vector? Well, this cannot be it because, or maybe I draw the vectors really as vectors here, not as dots. So from this point I can add this positive root and still get a weight, so this is not the highest weight, and so on. And I can easily see that this is the highest weight. All right, because whenever I add any of my 3 positive roots, I get out of the diagram, so here this property is fulfilled. Yeah, so why are these, okay, and here it's just the example, but the theorem states definition and theorem. Right. The theorem states that I always find such a highest weight, and it's uniquely determined in every case. So how does this help with the classification? There is a simplicial cone. Say C in H star R. So this is this Euclidean space in which the root system lives, such that I consider the irreducible G modules up to isomorphism. So two representations are considered equal if they just differ by a base change. And this is in bijective correspondence with the set of integral points in this cone. So again, P is the set of this weight lattice. So this is the lattice of all linear forms which can possibly occur as weights in any representation. And well, C is any cone in this Euclidean space, so we just take the integral points of this cone with respect to this lattice. And how does this go? Well, I just send V to this uniquely determined highest weight vector. Of not vector, sorry, the highest, just the highest weight itself. So that's it. So maybe also the names, definitions. C is called the dominant cone. Or the fundamental wave chamber. So maybe we also have a look at our favorite example. Where G is SL2. Right, so because there we know the left-hand side of this correspondence, we know the irreducible representations. These are just the VKs, so they are formed by these homogeneous spaces of homogeneous polynomials. So H star R. So how about, say, V2? Let's say here is omega, 2 omega, minus omega, minus 2 omega. So V2 has the weights 2 omega, 0, minus 2 omega. And which one is the highest one? Well, of course, 2 omega. Then there is V3. This has 3 omega, omega, minus omega, minus 3 omega. The highest one is this one. Maybe some boundary cases also. There's V0. This is just one-dimensional and has and the weight of this one-dimensional space is 0. So I guess you can see that I can produce every non-negative multiple of omega, because this will just be, well, say, let me just write it down. the highest weight of V. K is just K times omega. So in this case, we know already from our previous calculations that this theorem holds, and C is just the positive axis, right? So take C to be this cone positive real numbers times omega. So this is in our picture just the positive half axis. Oh. Right, and then this weight lattice P is just the lattice generated by lambda. So the integral points, so that the points I get here are the other points which are on this side, to the right of the zeros, because they are in C, and they are multiples of omega. So here we can just verify this. Well, and it's a theorem that this holds for general semi-simple Lie algebras. Did I want to say something else? No. The notation for this map. 5, 6, 5. I have this theorem 6.5 and I have this bijection, and I usually need a notation for the other way around, given what people then call a dominant integral weight, right? Because it's in the dominant cone and it's integral with respect to this weight lattice. So for lambda in this cone and also in this lattice, so what people call this is lambda dominant and integral, because it fulfills both conditions, the dominance conditions being in C and the integrality condition being in P. I denote by V lambda the up to isomorphism, of course. So this is almost uniquely defined. The irreducible G module with highest weight lambda. So note now we have a funny joke for G is SL2, V K is just another thing as V K omega, right? So actually this is where the notation comes from. To be precise, one should denote these modules by V K omega, because this is well, what it is about, but somehow there is the convention just to have this canonical basis element omega, and then one identifies P with Z. So for this special case, there is this parameterization of irreducible modules by numbers, but in general you would always have a parameterization of irreducible modules by these dominant integral weights, so by some particular linear forms on the carton. Good. So yeah, now that we know the classification of irreducible representations, there is of course the question, what are the characters? So now we can state very precisely what does it mean to understand the representation theory of a semi-simple algebra. We know the irreducible representation. Somehow we agreed that knowing a representation means knowing the character. And so the question is, so given, well, G, H were given for the entire chapter, but now also a dominant integral weight. What is the character of V lambda? So that means what are the dimensions of the weight spaces into which V lambda decomposes? And the answer is, well, there are several answers. But one answer, maybe the oldest one, by Hammer and Weil also. Yeah, so let lambda be a dominant integral weight, and then the character of V lambda is given by the following rational function. So the sum is over all elements of the Weil group. Maybe well, let me write it down. E to the W lambda divided by product over all positive roots 1 minus e to the minus W alpha. So that's the formula. But let me explain some things. So first we call the Weil group. That was this subgroup of the group of automorphisms of H star, or even they were even all isometries. And it was the group generated by the reflections along roots. Right, so this was by definition the Weil group. Well, and as the Weil group acts on H star, of course, then this means just the linear form I get if I apply this isometry of H star to lambda. And, well, then there is this stupid fraction. So if you think about characters as functions, then this is just a meromorphic function, and it turns out that all the singularities are soluble, so it will be actually an honest holomorphic function. But you have to study this a bit to notice this. Or if you prefer to view characters as formal objects, or you can make sense of this also, but maybe you want to think a bit about it then. Right, so, but there is a very explicit answer which computes the character and expresses it in form of this rational function. But then, of course, you can argue, so how good this is, because in order to, well, so note in order to find a particular weight multiplicity, so well, this is a generating function. So if I want to know the dimension of a particular weight space V lambda mu, I would have to expand this function. So I have to expand the character. For the character, I have this rational expression, so I would have to expand this rational function. And this is, of course, not so clear how to do it, or so from, I think from an algorithmic point of view, if you really want to know, have an algorithm given lambda and mu, what is this dimension? Yeah, it's not too useful, but it's still nice to have this closed formula for the character. So I briefly want to mention another ansatz, because this is from my thesis. And yeah, so how does this work? So there is the following theorem from Gelfand-Tsetlin. So there's always this ambiguity, because this is actually this letter, or I can't draw it so well. And so people either transcribe this as TS or Z or C. So whenever you see any of these, it's probably the same guy. And what do they say? So I consider SLN C. Then there is a family of polytopes. Say G. So this is from the other convention, so I abbreviate this as GZ. Lambda. So polytopes in R to the n times n minus 1 half. So parametrized by these dominant integral weights and a projection, or projection, a linear map. I think of it always as a projection. So it's just a linear map, pi from this space and to the weight to H star. Such that. So again, I want to have a character formula for V lambda. Lambda is a dominant integral. So V lambda is some irreducible representations. Its character is some function. So, and I consider the sum of all integral points in the Gelfand-Tsetlin polytope. Right. So now this is in R to the something. So by integral points here, I just mean all the coordinates are integers. And e to the pi of x. So it's not a projection in the mathematical sense as being a linear map such that it coincides with its square with respect to composition. So, but how do I think about those? Well, here I have Cartan dual H star R, and then there is still this R to the n times n minus 1 half, and there is this polytope somehow, this Gelfand-Tsetlin polytope with respect to a given lambda, and then there are some integral points, maybe that's it. The next ones would also already be outside of the polytope. So then I have this map pi, which just sends everything down. So this has two. So in this example, for example, this has two pre-images. So here we would conclude that the character of v lambda is, say, I don't know, say this is omega, this is 0, this is minus, or this is 2 omega, this is 0, this is minus 2 omega. Well, I just made up this example, but how would we interpret this? The character is just e to the minus 2 omega plus, then e to the 0 summons. There are 2. I have to sum up all e to the value of the projection, as these points are both sent to 0. This would be 2 e to the 0 plus e to the 2 omega. Right? So as we know, there doesn't exist an irreducible module with this character, because we just, so this is a fake example, but just to give you an idea of how this works. So and why I think of this as projection. You have this polytope, and then there are these integral points, and so by pushing everything to the dual of the Cartan and taking care of multiplicities, you get a character. Yeah. So what we talked about is the evaluation. So this is a corollary, if you want. So if you want to know the dimension of v lambda, so I don't pick any particular weight space, but I want to know the dimension of the entire module. So this will be the sum of the dimensions of all weight spaces. So I get this by evaluating the character at 0, right? So I have this formal, or as you want, formal or non-formal expression for the character. Anyway, a character is a sum of a linear combination of terms of the form e to the something. If I plug in 0, then each to the something becomes 1. So for each dimension is counted exactly once. So this is just the number of integral points in the Gelfand-Tsetlin polytope. So I get this dimension formula for irreducible representations of SL and modules just by counting integral points in this particular family of polytopes. So, and this has also generalizations, this theorem, to arbitrary semi-simple Lie algebras. Maybe I write this down. Arbitrary G semi-simple, and this is Littleman 89, 98, 90, I think 98. Do you remember? Do you know? No. Anyway. Well, but I want to talk about this, so it's a bit more complicated and uses much more involved theory. So this proof of this is elementary, or well, rather elementary, compared to the generalization. So I won't talk about this, but I want to talk about my thesis now. So there is this definition of a combinatorial definition of a vector partition function. So this is something, you can make a big bar here, now to something completely different. Just some combinatorial trick. Given vectors v1 through vn, say in n0 to the capital N, just some tuples of non-negative integers. I define the following function capital phi from n0 to the n, so the vector space in which these live, or in fact I can define this on the whole z to the n, and this will produce non-negative integer by, well, I have to say what's the value of some vector v, and that's the number of, well, let me just write it down as a formula first, and then I explain what it means. That's the number of c in n0 to the lowercase n, such that c1 v1 plus cn vn equals v. Cardinality of this set. So this is the so-called vector partition function associated with this list of vectors v1 through vn. So why is it called vector partition function? Well, what do I do here? I partition this vector into a sum of other vectors. So the idea is I have given some elementary vectors which are fixed once and for all, and then given any new vector v, how can I decompose this as a linear combination of the given ones, well, with non-negative integral coefficients. And you want me to do an example? Okay. So my favorite example actually is the following. So what are the vectors v1, v2, v3? These are just, well, so maybe I just should first determine n is 3 and capital N is 2. So we partition two-dimensional vectors, and we take 3 basic vectors into which we partition, and this should just be E1, E2, and E1 plus E2. So these are this one, this one, this one. So maybe I can so what is phi of the 0 vector? So how, well, let me draw a picture. So I have this lattice Z2, and I have these elementary steps. So, well, if you visualize this geometrically, this means starting from 0, how can I get to V only using these elementary steps and neglecting the order in which I go these steps. So if I start at 0 and I want to get to 0, I have only one possibility, not moving at all, because once I move, I can never go back, because I can only go to the top and to the right. So mathematically speaking, I have to put all these coefficients to 0. So there is just one possibility, just one coefficient vector. So this would be 1. So let's do some more complicated examples. So how do I get here? So this is v of phi of 1, 2. So here there should be more possibilities. I could go like this. This would be the linear combination. So what would be the corresponding C vector? I use the E1 once. I use the E2 twice. And I use the E1 plus E2, the diagonal one, not at all. Then I could use this possibility. So what's the corresponding V vector here? I don't go to the right at all. I go up once. I go diagonally once. And what's the third possibility? I can start by going up, and then I go diagonally. So I go up once, I go diagonally once, and I don't go to the right at all. And then you can just notice that these are all possibilities, so phi of this is 3. So it's just a... Did we? Oh, then we did something wrong. Yeah, this shouldn't be true. So we go up once. Okay, yeah, you're right. This. Well, but what? So I happen to have done this example many times earlier, and I know that there must be 3 ones. So I'm just confused now. Well, what's the third possibility to get there? Ah, no, it's not. Okay, that's all. Sorry. It's just the 2. Yeah. Right, thank you. So, yeah, as you pointed out, the green one was just equivalent to the blue one because we do not take the order into account in which we go these steps. So it's just 2. Yeah, anyway, so this is a nice combinatorial tool which is also useful in other situations. So if you have a certain function, sometimes it's possible to express this in terms of such a vector partition function with suitably chosen v1 through vn, and then there are theorems about these kind of functions which you can apply and then learn more about your original function. So this is why this might be a good trick to do. And the theorem then is the following. So again, given semi-simple Lie algebra and a Cartan subalgebra H, there exists a linear map from might be, or not, I'm certainly stating this slightly wrong because there's a technical specialty which I don't want to go into now. So I find a linear map from P, Cartesian product with P to some vector space or to some set n0 to the n for some n. Yeah. So there exists an n and there exists a linear map, say B, and there exists a vector partition function phi defined on this space so I can, in other words, I can find suitable v1 through v little n such that the dimension of v lambda mu, so the dimension of such a weight space, is given by as follows. I take lambda mu, so lambda and mu are both weights or contained in this weight lattice P. This is just a tuple. Then I apply the linear map, now I'm in some n0 to the n space, so I can apply this vector partition function to this space, and that's it. So here this trick succeeds. One can construct such a linear map and such vectors v1 through v little n, and gets this expression of the weight multiplicity function v1, so the function which associates with any two weights lambda mu the dimension of the weight mu weight space in v lambda, and you can express this function with this formula. So and right exists, but the construction is explicit. So for small examples, I can also compute this matrix or this linear map B and also these vectors v1 through vn and do everything very explicitly, but it's still a nice. Good. Yeah, and now I want to comment on the third character formula by Demazure, because yeah, I was just thinking about these recently, and I'll explain something about this in a research talk on Friday. So if any of you wants to come or can make it, I want you to have some background information about these also. So let's, as usual, G be semi-simple, H Cartan, delta a base of the root system. So that's a bit bad, using capital Phi for the, so now there will be no vector partitions functions occurring anymore. So capital Phi is the root system. So if alpha is any of these elements of the base, which are, I don't remember if I introduced this name, they're called simple roots. So once you have fixed the base for a discussion, then the elements of the base are called simple roots, and well, because these are the ideas. These are the simple roots, and the others are then the composite roots, which you get as a linear combination of the simple roots. So if alpha is an element of the base, I define Demazure operator D as alpha, so it's indexed with a reflection along this simple root, and this is a linear operator from CP to CP. So recall this CP is the space of linear combinations of expressions of the form. Just repeat it. So this is space of linear combinations of expressions of the form e to the lambda, where lambda is an element of P. So this is actually an algebra. You can define a product here, but for this discussion we don't need the product, but we just view this as an infinite dimensional vector space, basis elements being indexed by elements of the weight letters. So how do we define a linear operator? In general, it's of course sufficient to define it on a basis. So I have to say what is D as alpha e to the lambda. So this is a basis element. Of CP. And then I can define the linear operator just by linear extension. So what's that? Sum from I from 0 to lambda alpha check. E to the lambda minus I alpha. Well, I'll do an example later. It looks a bit complicated, and it actually is, but it's not too bad. So this holds if lambda alpha check is non-negative, then this sum actually makes sense. Lambda alpha check is 0, then it's just 0, right? So it's somewhat it's intuitive. If this angle bracket expression gets smaller and smaller, the sum gets shorter and shorter. If it's 0, there's just one summand left. If it gets here I'm doing something wrong. If it gets -1, then there is no summand left. So this should be 0. And if it's even smaller than -1, then I do the following stupid thing. I say, well, it's as you define. The idea is the same if you define a function, Riemann integral f on x dx ba, if this is just minus integral ab f on x dx if a is smaller than b. Right, so this is a usual convention you have in calculus, and somehow we try to imitate this here. And here it's always a bit more confusing because you can make things wrong with the boundary conditions. So I think it's I from -1 to, or from lambda alpha check +1 to -1 e to the lambda minus I alpha. No? So let's do an example. say G is SL2. Then you have your H R star is just a line. And we have 0, omega, 2 omega, 3 omega, minus omega, minus 2 omega. Then this 2 omega is also alpha, or so we have two roots here for SL2, minus 2 omega and 2 omega, and I choose this usual choice to be that the delta consists of the root 2 omega. So and then do we do this? What are these level or hyperplanes, which are just level points here? So here I don't draw it in the picture here because level points are somehow stupid. I just say it holds k omega alpha check is just k. So you can verify this if you want. So what is ds1? So maybe ds alpha. So what's that? Say I evaluate it at e to the omega. So I have to calculate omega alpha check, which is according to this rule k. Or maybe I can just prove this as we don't have these exercise sessions anymore. So this is a nice exercise. What's the k omega alpha check? Well, this is just by definition 2 k omega alpha divided by alpha alpha. So let's have to normalize the invariant product. Okay, I notice I'm talking too much things now I didn't discuss. Let me not finish this. So anyway, as a matter of fact, I can show this property, and so this is just 1. So what I get is e to the omega. So it's 1, so we're in the first case. So I have to subtract the number of alphas. Here I subtracted 0, and then I have to subtract 1. So this is e to the omega minus alpha. And well, this is just minus omega. So this is e to the omega plus e to the minus omega. So how to think about this? Again, this CP is just a vector space with bases E lambda. So here I wrote linear combinations of basis vectors, but of course I can just think of elements of this vector space as tuples of integers. Now, or as I do, if I usually have, if I fix the basis in the vector space, then vectors just become tuples of tuples of real numbers if it's a real vector space. So how you can think about this is, well, of course, these are infinite tuples now. This space, this is just Z. So what's this vector we started with? That's e to the omega. So almost all coefficients are 0. The one coefficient is 1, the one corresponding to e omega. So maybe I call this the first coefficient. And this is sent by this Demazure operator to, again, an infinite vector, which consists mostly of zeros, and then there are two ones, precisely 1, 0, 1, 0, all the other is 0, right? So this is the first coefficient. And this is the minus first coefficient. Now let me just do some more examples. I'm not sure how well this is understandable, but time is almost up, so I will continue this and give some better explanation on Thursday. So how I like to think of this is, well, this is the row vector, infinite row vector. And somehow this Demazure operator gives me a rule how to fill out this row vector. Here the coefficients are numbered by -2, -1, 0, 1, 2, 3. And what this rule says, just if I have a 1 here in position 1, then this produces another one over here. Right. Or if I have a 1 at position -1, -1, 0, 1, 2, 3. So on the top I write the indexing of the coordinates. So if I have a 1 at the position -1, well, then I'm in the second case of the definition of the Demazure operator, which I erased. So this vanishes. So this is just the 0 vector. And if I have a 1 in some negative coordinate, say -2, so if I have a 1 in a positive coordinate, this produces -1s to the left, and if I have a coordinate in the negative, and the 1 with negative coordinate, this produces 1s to the right, -1s to the right. So -2, 0, 2. This would produce a -1 here. Demazure operators also open only with this. So I won't talk about this background, but just explain these as rules how to fill up a diagram like this, or Friday diagrams will be infinite matrices. So this will be a two-dimensional or rank 2 example. Then you have infinite matrices, and you have a certain rule similar to this one, how how ones there will produce other ones, or one here will produce minus one. And but then on Friday I won't explain the relation with representation theory, but on Thursday I will explain how this rule helps to compute characters of